The name of today's lesson is Rational Numbers, and we're going to start by going over our vocabulary. Today we have 3 vocabulary words. The first one is rational number. The rational number is a number that can be written as a quotient of 2 integers. Basically what that means is a number that can be written as a fraction, because as I say in class all the time, fractions are division problems. Our second vocabulary word is a terminating decimal. Terminating decimal, is exactly what it sounds like. It is a decimal that has an end It means that when you are dividing, the division stops. And the second kind of decimal we'll be looking at today is a repeating decimal, and that is a decimal in which a single digit or a block of digits repeats without end. And what we'll do as we go through our 5 or 6 examples is we will see different examples of terminating and repeating decimals. Let's take a look at our first example. To show that the number is rational by writing it as the quotient of 2 integers. When you see all these words, boil it down to this. Write each number in a fraction form. That's all you have to do. So when we have a -5, the way to put that into a fraction is to put the -5 in the numerator and the 1 in the denominator. And if you wanted to check your answer, you could look at this and say, well, if you ended up with this answer, say, as the solution to an equation, and you had -5/1, you would simplify that to a -5. And then when we have a mixed number, a number with a fraction, what we have to do is turn that into an improper fraction. If you remember, the way to do that is to take your denominator and multiply it by your whole number there. 4 times 8 is 32, and then you add to it the numerator. So our numerator is 33, and we keep the same denominator, which is 4. 8 1/4, represented as a fraction, is 33/4. Now let's take a look at example 2. In example 2, we have to take the fraction and we have to express it as a decimal. Again, fractions are division problems. So that's what we have to do. We'll be doing a lot of division in these next few lessons because we will be working almost exclusively with fractions. And the way to divide the 5 and the 8 in the fraction 5/8 is that you take your numerator, and that goes in your house, so to speak. It's numerator divided by denominator, 5 divided by 8. And then we have our 8 on the outside. Now you can see right away that 8 doesn't go into 5. But you knew that anyway when you saw this. 5/8 is a number that is less than 1, which means that your answer is going to be a decimal that is also less than 1. So before we start doing any division, we put our decimal here next to the 5. After we put it next to the 5, put it immediately above that into our quotient space. And then what we'll do is I'll annex a couple of zeros. We won't know how many we'll need. And then we can start our division. 8 does not go into 5, so I'll put a 0 there as a place filler. But 8 does go into 50 6 times. 6 times 8 is 48. Bring down our 0. And now we have 8 going into 20. That's twice. 2 times 8 is 16. And we have a 4. Now the key to this, even though this skill is something you learned probably as far back as 5th grade, I want you to understand that we're not going to be using a remainder. We want to take this as far as we can. We need to see if this decimal will either terminate, if our division will end, or if we'll have some numbers that repeat. So what we're going to do is I'm going to annex another 0, and I'll bring that down and put it next to our 40. 8 goes into 40 5 times. 5 times 8 is 40. we ended up with 0. Our division ended. So 5 divided by 8 is 0.625, which means that the decimal equivalent of 5/8 is 0.625. And then we're going to do the same thing for part B. In part B, we have to show the decimal value of 4/9, and we'll do it the same way. We have 4 divided by 9. Right away, I'll put in my decimal points, 1 immediately following the 4, and then 1 right above it in the quotient area. And I'm going to add a couple of zeros, and then I'll start my division. 9 doesn't go into 4, but 9 does go into 40 4 times. 4 times 9 is 36. We subtract. We bring down our 0. 9 goes into 40 4 times. 4 times 9 is 36. We have this difference of 4. And you can already see what's happening. If we were to annex another 0 and bring it down, we would end up with a 40. 9 goes into 40 4 times 36. So this is going to go on over and over and over again into infinity. And what do we have? We have 0.4444 into infinity. And the way that we express this is we call this a repeating decimal. And we write the answer this way, 0.4. And then what I do is I draw a bar directly above the 4 because that number 4 will get repeated. And we're going to do just one more. Here we have 1 and 2 11ths. And most often, when you're working with mixed numbers, you will very often turn them into improper fractions before you work with them. And just as we did in example 1, we are going to turn this fraction into an improper fraction by multiplying the denominator and its whole number. 11 times 1 is 11. We'll add to it the numerator, which is 2. 11 plus 2 is 13, which gives us 13 divided by 11. Beyond that, the steps are exactly the same. I put in my decimals, and I'll annex a couple of zeros, and then I'll start my division. 11 goes into 13 one time, and then we subtract, and we bring down our 0. 11 goes into 20 once. 1 times 11 is 11. That gives us a difference of 9. Bring down a 0. 11 goes into 90 8 times. 8 times 11 is 88. That gives us a difference of 2. We'll annex another 0. 11 goes into 20 once. 1 times 11 is 11. We'll do our subtraction. We'll get 9. Annex a 0. We have 90. 11 goes into 98 times. So you see what's happening. We have another repeated decimal. 1 and 2 11ths is equal to 1 point. Now what's happening here? We have 1 8, 1 8, and that will go on into infinity. So when I write my answer, I'll write 1.18, and then my bar will go across both the 1 and the 8 because it's both those numbers that get repeated. So here we're switching gears a little bit. We're going to start with a decimal, and we want to write it in fraction form. This is what we're doing in example 3. So what you're going to need to do is remind yourself of the place value of all the digits that follow the decimal. This first place after the decimal is the tenths. The second place is the hundredths. After that is the thousandths, 10,000ths. So when we take a look at this, we have 0.15. when we change it into a fraction, you have to first realize what this number is. And it's, if you were to read this, instead of saying 0.15, you would say 15 hundredths, because this ends in the hundredths place. 15 hundredths. And then just as we have to do every time we're working with a fraction, is we have to write it in its simplest form. I can see that 5 is the greatest factor of 15 and 100. There are 3 5s in 15 and 20 in 100. So 15 hundredths expressed as a fraction is 3 over 20. Let's take a look at this. When we read this, we say -4 and, because that's what the decimal means, 2 hundredths. And we're going to write it, well, quite frankly, exactly the way that it sounds. -4 and 2 hundredths. And I see that both 2 and 100 are even numbers, which means that can be simplified. Our final answer is -4 and 1/50th. And this is the fraction equivalent to this decimal, -4.02. And we have one more, 2.175, which is 2 and 175 thousandths. And of course, we have to simplify it. Our 2 stays the same. The greatest common factor of 175 and 1,000 is 25. 175 divided by 25 is 7. And 1,000 divided by 25 is 40. And so this is our final answer. 2.175 in a fraction is expressed as 2 and 7/40ths. That's what we do when we're working with the terminating decimal. These next 2 examples, though, are going to involve taking a repeating decimal and showing it in a fraction form. It's a little bit complicated. There are a lot of steps to it, so pay special attention. And when we are in class tomorrow, we'll go over it further. Just pay attention as best as you can. Make sure you take good notes. I'll try to make it as easy to understand as I can. So write the repeating decimal as a fraction. When we have a repeating decimal, we have this one is 0.5. And what we want to understand first is that this means 0.5555 into infinity. Now what we're going to do for this method involves calling this x. Anytime you have a repeating decimal and you're going to convert it to a fraction, the decimal that you're given is called x. And so our goal is to come up with a problem in which we can easily move this into a fraction. Now here's what we're going to do. This involves some subtraction. We're going to multiply this, every piece, by 10. We're not changing it. We're not changing its value. We're just changing the way that it looks. We're making an equivalent. So 10x means 10 times 0.55 repeated. Remember when you're multiplying a number by 10, you move the decimal point over to the right once. So instead of 0.5555, we end up with 5.5 repeated, which, just to be very clear, is 5.555 into infinity. Now that we have designated our x and multiplied it by 10, I'm going to show you what we're going to do. We're going to set up side-by-side subtraction problems. So we're going to have our 10x, and we're going to subtract from that our original x. And on the other side of that, what we're going to do is write down in decimal form what the 10x and the x are equal to. Our 10x is 5.555 repeated, and our x is 0.555 repeated. 10x minus x gives us 9x. 5.5 repeated minus 0.5 repeated. Even though these go into infinity, they're exactly the same. You can see all the 5s are lined up. So these will become 0. 5 minus 0 is 5. So now what we have is 9x equals 5. And this is a very simple one-step equation. We'll divide both sides by the coefficient 9. Here we have x isolated. It has the coefficient of 1. And we have determined that x is 5/9. Our original x is 0.5 repeated. Our fraction form of that repeated decimal is 5/9. Now what we're going to do in our next example is do a problem like this. Be a little bit more complicated because the repeating decimal is in a different place, but we're going to be following the steps. Just to recap what we did here in example 4. We took our original repeated decimal that we were given, and we named it x. And then what we did is I multiplied it by 10. And the reason I multiplied it by 10 is so that I could get this 0.5555 to be the same in both our numbers. I wanted to end up with a product that had exactly the same number of digits following the decimal as I did in my original x. Then we subtracted the 2 and we divided by the coefficient. As I said, we'll do this in our second example. So I hope you can read this clearly enough. Our number is 3.76, and the bar is above the 6. That means the 6 gets repeated. So let me be very clear. That means it's 3.76666 repeated. And we're going to call this x. And so what we want to do is we're going to multiply this until we can get our digits following the decimal the same so that we can subtract them. So if x is 3.76 repeated, 10x would be 37.6 repeated, which would be 37.6666. Now you see, when I multiply this by 10, our numbers following the decimal are different. This is 0.76666, and this is 0.66666. And when that happens, what you do is you multiply your original number by the next 10. Because what we want to do, in case it wasn't clear before, is we want to have two numbers that have the same exact digits following the decimal so that we can get rid of them, so to speak. So 100x times 3.76 repeated is 376.6 repeated. And when I show that, what that means is 376.6666, and these are all repeated. So before we get any further, because I know that this is confusing, here's what we're doing. We have our original decimal, which is 3.76 repeated, and we're calling that x. And what we are doing is one step at a time, 1/10 at a time, making equivalent fractions, making equivalent variable expressions. So if x equals 3.76 repeated, 10x is 37.6 repeated. And the reason we took it another step, we multiplied and found out what 100x is because we needed to do that in order to get two numbers that have the same exact digits after the decimal. We had to multiply by 100 in order to get 0.666 repeated in both of these numbers. So what I'm going to do is, now that it's time to set up our subtraction problem, I'm going to take, you always put the larger number at the top, so I'm going to take my 100x, and I'm going to subtract from that my 10x. And then, if you remember from example 4, the example right before this, I also include what the equivalents are, what the values of these are. 100x is 376.666 repeated. 10x is 37.6 repeated. And we subtract. 100x minus 10x is 90x. These 0.6 repeated end up being 0. 376, well, we'll have to regroup. 16 minus 7 is 9. 6 minus 3 is 3. 3 minus nothing is 3. And then we divide both sides by the coefficient 90. And we get x equals 339 over 90. But we cannot keep a fraction like this. We need to simplify it. I'm going to move up here for that since I've run out of room. So we have 339 over 90. This is an improper fraction. There are 3 90s in 339. So we'll have a mixed number as an answer. Our answer will be 3. And let me see, 3 times 90. Pardon me, is 270. That will give us 69 90ths, which simplifies to 3 and 23 30ths. And that's our final answer. And now for our last example. Now what we're going to do is combine what you know about integers and what you know about ordering decimals, and what we just learned about turning decimals to fractions and fractions to decimals, and ordering these 6 numbers. Here we have 0.21, 2.3, 8/3, a negative 0.1, a negative 1/5, and a negative 0.2 repeated. Now the first thing that we need to do is have some consistency before we can compare these numbers. And so we are going to be using decimals. Now this 0.21 doesn't need to be changed at all, so I'm just going to bring it down exactly the way that it is. Same thing for this 2.3. There's no reason to do anything to it. But notice here I have 2 places after the decimal. I'm just going to fill that in. I like to have everything even. 8 over 3, 8 divided by 3, you'll find when you do your division, is 2.6 repeated. So I'm going to, again, keep 2 decimal places. Negative 1/10, well that will stay the way it is, but I'm going to annex a 0. Negative 1/5, when you do your division, you'll find, excuse me, is a negative 0.2, and I'm going to annex a 0. And then a negative 0.2 repeated is negative 0.22, and that repeats. Now I see that I have a combination of some positive numbers and some negative numbers, so what I'm going to do is identify my negative numbers first, because we have to order these from least to greatest. So we have a negative 1/10, we have a negative 2/10, and a negative 0.22 repeated. Now, when we are ordering negative numbers, you remember it's almost counterintuitive that we rank the numbers by what looks bigger first, because what looks bigger when it's negative is actually a smaller number, which means that we have our negative 0.2 repeated first, followed by negative 0.2, and then our negative 0.1. Now we have three positive numbers. We have a 0.21 and two numbers that are greater than 2, so we know right away that our 0.21 is the least of those two. 30 hundredths is less than 66 hundredths, so our 2.30 comes next, followed by our 2.6 repeated. The main point that you need to remember when you're ordering numbers is, as I said before, uniformity. Either put them all in decimal form or all in fraction form. I opted for fraction because it's easier to convert, in my opinion, fractions to decimals. And decimals are very clear, especially when you annex the zeros and you have all the numbers filled.